Polar coordinates. This lesson is going to focus on how to graph polar coordinates, also to go in between polar and rectangular coordinates, conversions, and also we will graph an equation. Let's first start off with this here. What you're seeing here is a point that has been graphed in rectangular form. In rectangular form, what it is that typically when you graph, you would go horizontal and then vertical. So we're just going to focus on that part of it here. Recall that there's an x value and a y value. The x value tells you how far you've gone horizontally. The y value tells you how far you've gone vertically. As you can tell from here, we've gone horizontally 3 units to the left. That's the negative direction. And then 2 units up. So we would write that as -3, 2. Polar, on the other hand, is a little different. So let's go ahead and map that on there. This is a polar graph, in that in the center here is considered the pole instead of the origin. Notice that point P here hasn't moved since I've matted that over. What we're going to do now is vanish the rectangular graph. So now all you can see is the polar. Now P hasn't changed at all, but the way in which we would describe how we get to P is a little different. With polar, the coordinates are not x, y, but rather r theta. And what we're doing is we're describing the radius essentially and the angle of rotation. To determine that, what you would do is you would go horizontally for the radius, same as x. Radius being positive would be to the right. Radius being negative would be to the left. The angle would tell you how far you would rotate. Now, if your angle is positive, you will rotate counterclockwise. If, on the other hand, it's negative, you go clockwise. Notice that point P is between the third and the fourth ring, which means that the radius is going to be somewhere in the middle, say probably 3.5. If we could draw a circle, it would be like that. So essentially, how would we get here? You get there several different ways. We could go to the right, however it is, 3.5 units, 3.5-ish, and then rotate however many degrees that is. And that would be a possible solution. What is unique about polar is that the points, the coordinates rather, to describe a point, there are infinitely many of them, and the reason why is because the number of angles that you can get. You can go around and around and around infinitely many times. With rectangular, on the other hand, it's always one unique point. Let's do an example here. Let's say you're going to graph point A being 2, 135 degrees. Well, to graph that, this is a positive radius, so starting from the pole position, you would go 2 rings across to the right because it's positive. And then you would count 135 degrees in the positive direction. And once you do that, you would place a point. So there you are. What is different from this is that you would just simply put the point. In the past, you would just draw an angle like this, and then you would say from here to here is 135 degrees. And that would be it. So when you used to graph angles, you would do all this. If it was a negative angle, you would go this way, but you would draw the angle essentially. Here you're not to draw an angle, just simply a point. Let's do another. B being 3, -60 degrees. Since the radius is positive, we again go to the right 3 units. And then since it's a negative angle, we're cycling clockwise. And hopefully you figured out by now all these lines here, they're 15-degree increments. The way you figure that out is that it's a 90-degree angle here and 6 regions, so 90 divided by 6. That means that 60 degrees is going to be right here at this location. So there you are. How about -4, pi over 3? You'll notice that this is in radians, so if you want, you can convert that to degrees, being 60 degrees. Or, if you're used to thinking in terms of radians, pi, remember, is halfway around a circle. So if you were to take a straight line and divide it into 3 pieces, that would give you a sense of how far to rotate. So -4 is in the negative direction, 1, 2, 3, 4, and then we cycle positive pi over 3 radians. Remember that positive is counterclockwise. So don't think of it as up or down. Think of it as clockwise or counterclockwise. So essentially, it's going to be located right there. One more for you. How about point D being at -2, -30? Again, just as before, the negative radius is telling you go left first, and then, since it's a negative angle, we rotate clockwise. So in that direction, essentially, that's what we're looking for right there. Now let's talk about getting an equivalent set of coordinates. Only this time, let's keep the radius negative, meaning that it's still going to be -2, but the angle making it positive. So consider, you still go across negative, but instead of rotating in the negative direction, you are going to rotate in the positive direction. How many degrees would that be? One easy way to do this is when you graph your point, just draw a line through it here, and then just identify the reference angle being 30 degrees. So if you understand that, how many degrees is it all the way around here? That's 330. So we can say -2, 330 degrees is an alternate set of coordinates that describes the same location. Let's do another, only this time let's assume that the radius is positive, and this time the angle between -360 degrees and 0. In other words, the angle is negative. Well, same strategy here. Graph that point first, and draw a line through so that way we can identify that reference angle. Since we're tracking the angle being positive, let's just start over. We are going to go across +2. So we know the first part is just going to be a 2 instead of just -2. And then since we're going in the negative direction, we just cycle around that way. How many degrees is that? That's -210. So 2, -210 would be an alternate set of points. Understand that there are several, in fact infinitely many coordinates that we can come up with to describe this location. We could have, for example, started over here and then kept going around like this until we wound up at that particular point. And the reason why is because you have infinitely many coterminal angles. Now let's talk about conversions. Let's say that we're given a point, 3, -3. That's in rectangular form, in that you would went across 3 and then vertically -3. How would you convert this to a polar point so that we would be representing a radius and a rotation? Well, let's first graph that point. Recall that the path that we use to graph a point would be to go horizontal first and then vertical, so I'm just simply tracing that path. Now here's what you want to find. You see this distance here from the origin to the point. Well, that's the radius of a circle that this point is on. We want to get the length of the hypotenuse for this right triangle. That would represent the radius. We're also going to need to know the reference angle. That's that angle right here that I'm shading in. Using the Pythagorean theorem, we would get 3√2 for the hypotenuse. As for the reference angle, let's use tangent. The tangent of that reference angle is the opposite over the adjacent. That's -3/3. If you tap that into your calculator, the arctangent of 3/3, what you get is 45 degrees. Okay, so now we're ready to write the point. 3√2, you'll recall, is the radius. As for describing the angle, we have several different ways of doing this. We could just simply go from here to here. That's -45 degrees. And that would work just fine. Or what typically happens is that a lot of times your instructor would prefer that you write the angle as a positive angle between 0 and 360. So if you get that angle to go with your radius of 3√2, that would also do as a solution, so 315 degrees. Let's do a second one here. Let's convert -1, 2 to polar. Just as before, we want to graph that point. And what you want to determine is the distance from the origin that point is located at. If you use the Pythagorean theorem, you get the square root of 5. Okay, now let's work on getting that reference angle there. Let's go ahead and use tangent again. So the tangent of that reference angle is rise over run, or opposite over adjacent. In other words, 2 over -1. So typing that into our calculators, the arctangent of 2, no need for the negative because we're just looking for a reference angle, And what we get is approximately 63 degrees. Okay, so let's finish this up. Assuming we write this with a positive radius, that is the square root of 5, then this angle we want will stick to positive. Since it's 63 degrees here for the reference angle, that means the rest of the angle has to be 117. And there you are. What about going the other way around, from polar to rectangular? That's actually easier. What you have are a couple formulas here that I'm showing you. X is equal to r cosine theta. Y is equal to r sine theta. Where they come from is from this triangle. This is x, this is y, and this is r for radius. X because that's the horizontal direction, y is the vertical direction. If you were to get the cosine of angle theta, you get x over r, that's adjacent over hypotenuse. And for the sine of angle theta, that's y over r. Now, if you were to take these two equations here and multiply out the fraction, in other words, multiply both sides by r, the r's would go away on the right-hand side, and you get r cosine here, which represents this formula. Multiply both sides by r here, and that represents this formula. That's really all you need to do this. Let's say that you wanted to convert this point to rectangular, 4, 150 degrees. Well, let's just go ahead and use our formulas. Recall that the x-coordinate is r times the cosine of theta. That's 4 times the cosine of 150 degrees. The reference angle for 150 is a special angle, 30 degrees. So that's really negative root 3 over 2. So 4 times that, and what happens is your 2 and your 4 reduce to become 2 and 1. What you get is negative 2 root 3. And as for the y-coordinate, it's the same thing. That's 4 times the sine of 150 degrees. Again, the reference angle is 30 degrees, so the sine of 30 degrees is a half, and it's going to be positive since we're in the second quadrant, and that reduces out to give you 2. So there you have it. Okay, let's graph an equation here. Graph r is equal to 1 plus the cosine of theta. Typically, when you get polar equations, it's in r equals form. So, a bit backwards. Now, what we're going to do here is we're going to come up with a table here, and with the table, since r here is the dependent variable and theta is the independent variable, I'm going to list the theta first. So, here are a list of numbers, and I'm going in 15-degree increments. You can go whatever feels comfortable for you here. And yes, we're going to do this the old traditional way of how you first learned how to graph, which is to just simply plot points one at a time. Hope you have your calculator handy. If you plug in 0, that's 1 plus the cosine of 0 degrees. In other words, 1. So 1 plus 1 is 2. And you just simply graph that point, which is what you're seeing over here on the right-hand side here. That's 2 for the radius, and then since we rotate 0 degrees, there we are. Plug in 15, and that's 1 plus the cosine of 15 degrees. That's 1 plus 0.97, which is 1.97, and I've rotated 15 degrees. 1.97 is close to 2, so that's why you're seeing it a little bit more inward. Connect your points. And then you just keep going and going and going. 1 plus the cosine of 30 degrees is 1.87, so a little bit closer to the pole. 1.7 for 45 degrees, and so on and so forth. Now, if you'll notice that this is beginning to curve. That's perfectly normal. So just go ahead and connect them. The more points you have, the more smooth this will be. And then just keep going. Now, one of the things you should recognize, though, is this. You notice how with this one, we get 0.3 again, just like up here, only this time it's negative. Keep in mind that the cosine is negative in the second quadrant. So that doesn't necessarily mean that we're going to do anything fancy here, but because you'll notice that 0.7 is still the radius, that's within the first ring here, and then you rotate 105. But traditionally, when we used to graph these things, we would draw an angle and such, and remember that all of them are positive in this quadrant if your angle is in here. But if your angle is here in the second quadrant, just the sign and its reciprocal would be positive. Moving forward, we get negative 0.5 for the cosine of 120, then finishing off the rest. Now, what you should notice here is that right here, these values are repeating in reverse order. And because of that, if you've gone through the trouble of putting this into your calculator, you should recognize that after that, you can pretty much see the pattern here. It just repeats, only in reverse order. So we had 0.3, 0.3, 0.5, 0.5. And all you have to keep in mind is the negative sign, because again, the cosine is negative in that second quadrant. So finishing up, if you were to do the rest, and we'll count all the way to 360, we get a complete picture. So you'll see that again, 0.3, and then 0.13, 0.03 rather, 0.13, 0.3, 0.5, 0.7, and that's again utilizing all these values again. So what we get is like a heart shape. And that's really all there is when it comes to graphing polar equations. Just simply plug them in. Typically you plug in for the angle and then graph the point and then connect. That's it for this one. I'll see you next time.